students, welcome back. This is Torres, Elbow Bump. How are you? Are you doing okay? Is your family okay? Remember, if you need anything, please send me an email so that I can try to help in some way. So lucky you, you get to hear my voice for another lecture. But the best part is we will be talking about types of hypothesis tests. Yay! In the last few lectures, we've been talking about null hypothesis statistical testing. So null hypothesis testing is a formal approach to decide whether the results of your sample actually reflects the real relationship in the population or if it's just happening by chance. When you're writing the null hypothesis and the alternate hypothesis, you have to make sure that both hypotheses are written in terms of the population parameter. The null should be the statement where there is no difference. So if things continued as they are, it's what we would expect to happen no matter what. The alternative states your question. So if you want to know if there's going to be an increase, if there's going to be a decrease, or if there's just going to be a change in general from what has been happening thus far. During a study, the researcher has the null hypothesis to start with, right? It's whatever they expected to see in the sample. If there is enough evidence at the end of the experiment, at the end of the study, that the treatment changed what was expected, then the researcher can reject the null hypothesis and retain the alternative hypothesis. In other words, they have this situation that is supposed to remain unchanged. And then something came along, a treatment, and they want to know if that treatment is going to affect this non-changing situation. There is enough evidence that the null has changed, and it cannot be due to random chance because it's so incredibly improbable. Then the researcher will reject the null and assume that the alternate hypothesis is correct, that the treatment had some effect and it was not due to random chance. So what we're going to do today is we're going to actually write out some hypotheses and use some examples so that you can see when you're going to retain the null and when you're going to reject it. The null and alternate hypotheses are written in terms of the population parameter. And the big idea that we've been talking about over and over again is we cannot see the population parameter. In most cases, it's impossible to see the population parameter. So we're using the sample and trusting that the sample is sufficiently alike to the population parameter that we can infer that what's happening with our sample is also happening with the larger population. So sometimes we can be correct about what's happening in the population, right? If the null hypothesis is true and we don't reject the null hypothesis, then we made the correct inference about our population. If the alternative hypothesis is true and we reject the null, then we made the correct inference about the population. But there's two times where we can make two different types of mistakes about the population. The first type of mistake is a type 1 error, and it's usually considered the more serious of the two errors in most situations. I can't think of any situations where type 2 error is more important, but I would say that it's still arguable. So type 1 error is when we falsely reject the null, meaning that the truth within the population that is unseen is that there is no change with whatever effect you were trying to study. And you thought there was and you rejected it. Type 2 errors happen when the null is falsely retained, meaning that there was actually an effect happening, but you were unable to detect it in your study. In order to control for type 1 error, you decrease your significance level. And your significance level is the amount of risk that you want to take in committing a type 1 error. Okay, that's your alpha. You said it at the beginning. In order to control for type 2 error, you have to increase your significance level. So you can see how kind of balancing these two out is really tricky. Because if you don't get it correct, then you're trying to balance how much you want to control for type 1 and control for type 2. The only way you can really control for both is by increasing sample size. That's really the only way to mitigate committing either type of error. So let's look at this in a little bit more detail before we go into our examples. So here I have a one-tailed test. Notice that whatever hypothesis this was, this line right here is going to be the z-crit. And it's the z-score that marks where the alpha begins. The gray is the proportion of the curve, the percent of the curve that marks your alpha. So if you have a 5% alpha, the gray is 5% of your curve. If you have a 10% alpha, the gray is 10% of your curve. So it depends on how much you risk, what you decide your alpha is going to be, in finding where your z-crit will be and where you can mark the area of rejection. So this alpha area can also be called the area of rejection. This is your model. So you've set up this model ahead of time, like a good researcher, and you said, okay, I'm setting this amount of alpha, say 5% alpha, pretty low error rate. And you decide, okay, I'm going to figure out what my z-crit is for 5% alpha. It's here. And then anything beyond that, I'm going to reject. Because anything that happens in this 5%, I'm going to reject. After you do your experiment and you have your results, then you can compare where your information hits on the curve. So you're also going to have a z-score for your test statistic. And you're going to compare your z-score for your test statistic with your z-crit that you set ahead of time. You're also going to compare your p-value, the expected probability, to your alpha. If your p-value is less than your alpha, then you can go ahead and reject the null. This is considered sufficient evidence to reject the null hypothesis. So, of course, all of this is applicable only if you have a normal distribution. So if normality is not stated in the scenario, you are expected to check for the conditions of the central limit theorem. When calculating the test statistic, you're going to calculate it in a way that's very similar to just calculating a regular z-score. So I'm going to discuss a test statistic for proportions to start. We'll do means in a bit, but we're going to work with proportions first. So in order to calculate the test statistic for your sample, you're going to take the observed proportion in your sample. From that, you're going to subtract the proportion you used to state your null hypothesis, right? Take that difference, and then you're going to divide that by the standard error. Since we're working with proportions, you're going to use this formula to calculate your standard error. So you're going to take the difference of the observed proportion from your null proportion, and then you're going to divide that by the standard error using the standard error formula for proportions. At first glance, this might look complex, but it's not that big a deal. We're going to walk you through it and you're going to do great. So, if you recall, the null hypothesis is always written with an equal sign. Okay, so here you note the null hypothesis, P is equal to the proportion of the null. Okay, P is equal to the proportion of the null. P is equal to the proportion of the null. Regardless of what type of study you're doing or what your question is, your null will always be phrased with an equal sign. When writing the alternative hypothesis, you want to look to see what kind of question are you asking. So with a two-sided test, you're looking to reject the null of no difference if your result, the proportion in your result, is either much lower than the one that's expected in the null hypothesis or much higher than what's expected in the null hypothesis. For a one-sided left right-tailed test, you are concerned with values that are much lower than what is expected in the population proportion. So you're looking to reject the null hypothesis if in your experimental results, in your study's results, you get a expected proportion that is much lower than the null. Finally, for a one-sided right-tailed test, you will only reject the null if the proportion that your study gives you, that the results of the study gives you, are much higher than the population proportion. Let's look at the two-tailed hypothesis. Here I have my set of hypotheses. I have the null, which is saying that the expected proportion is whatever that population parameter proportion is, some proportion. And then I have the alternative hypothesis, which is asking the question, is the proportion in my sample significantly lower or significantly greater than the expected population proportion? So now, as part of the preparation for this, I have to decide how much am I going to risk in committing a type 1 error. Okay, so I have to figure out what would be my significance level, my alpha. Okay, let's just assume, just to make things really simple, let's just assume I'm going to risk 10% chance of committing a type 1 error on my two-tailed hypothesis. Because I have two tails and I want an alpha level of 10%, 5% has to go in my lower tail and 5% has to go in my upper tail, so that these two dark gray areas are taking up the whole 10%. It's not 10% and 10%, so it's 20% total. It's 5% and 5% for my 10% alpha. So if you have a two-tailed test, your alpha is going to be split in half, put in each tail. I have my Z-crit, which is this red line right here. I have my Z-crit, which is going to mark the Z-score that corresponds with my alpha, so that I know that everything that's less than my negative Z-crit and everything that's more than my positive Z-crit is going to mark my areas of rejection. So anything from here down is going to get rejected. Anything from here up is going to get rejected, okay? Anything that falls in this center area, I'm going to retain the null. So reject the null from negative Z less, reject the null from positive Z up, and anything in the white area means retain the null. There is not sufficient evidence that we should reject the null, okay? When we compute our test statistic, the Z-score for our sample, we're also going to need to figure out what the probability is of obtaining that Z-score. And that probability is called the p-value of your test statistic. The p-value is a probability, okay, and it assumes that if the null hypothesis is true, then the p-value is the probability that if this experiment were repeated, you would get a statistic as extreme or more extreme than the one you actually got. If you have a very small p-value, a very small chance of this happening, that suggests that there's a surprising outcome and that there is enough evidence that the rejection of the null hypothesis is okay to do. Okay, so you're going to reject the null if you get a very, very small p-value. You want your p-value to be less than our established alpha. So how do we calculate the Z-crit? Well, the Z-crit we get given, okay? So if you have a proportion, you've gone through the conditions of the central limit theory and they apply, then you can choose your significance level and the Z-crit for those are given to you. So if you have a significance level of 0.001 for a two-tailed hypothesis, your Z-crit is going to be negative 3.3. So your Z-crit, instead of like being over here, it's going to be way down here. And it's also going to be positive 3.3. So it's going to be way up here. So it's saying, here is my Z-crit. Anything greater than positive 3.30 or less than negative 0.30 gets rejected. Okay, see how that's really hard to do? Look at how tiny that little probability is. If you have a significance level of 0.01, so 1% alpha, and you have a two-tailed hypothesis, then half of the significance level would go here and half of the significance level would go here, right? So that both areas would be 1% total, so 0.5% and 0.5%. In this situation, you would mark your negative z-crit as negative 2.58 and your positive z-crit at positive 2.58 because, they're symmetrical, right? So in this case, your area of rejection would be anything that's less than negative 2.58 or anything that's more than positive 2.58. If you have a significance level of 0.05, then you have a z-crit of positive negative 1.96. Where have you seen that number before? You probably saw it as the multiplier for the confidence intervals, because confidence intervals are going to mark that center 95%, right? And 100 minus 95% is 5%. This is a 5% alpha. You have 2.5% in the left tail and you have 2.5% in the right tail. Anything that is less than negative 1.96 is rejected. A test statistic that is more than positive 1.6 gets rejected. Finally, a significant level of 0.1, which is a 10% alpha, is going to have a little bit greater z-crit. You would get a z-crit of positive negative 1.64, meaning that any test statistic that is less than 1.64 would be rejected, and any test statistic that is greater than 1.64 would be rejected. Okay, so let's look at an example on Ziteboard. Okay, so here I have a very simple scenario. We're just going to use a random proportion. I just happen to pick a proportion of the population that prefers red cars. Okay, we're just going to keep it super simple, nothing complex, just who likes red cars. Okay, and we want to know, has the proportion of the population that prefers red cars changed from 17%? So at some point, there was some study done that some proportion of the population liked red cars. And we want to know if that's changed. So because it says it's changed, there's enough to say that we want the alternate hypothesis to show that there's just any change. It's not specifying whether it wants to know if it's decreased or increased. We just are looking for a change. Okay. So the next thing we need to do is we need to decide on an alpha level. Let's just try an alpha level of 0.05. So the z-crit for an alpha level of 5% is positive and negative 1.96. Positive and negative 1.96. So if we look at our curve right here, positive 1.96 is right here next to 2. Okay, that's my z-crit. That's a positive z-crit of positive 1.96. Okay, so anything past this, past my z-crit, I'm going to reject. Okay, but I also have a lower z-crit. That z-crit is anything below negative 1.96. So negative 1.96 is again very, very close to positive 2. Okay, it's right here. This z-crit is negative 1.96, and I'm saying anything less than this, I'm going to reject. Now, I'm not a very good artist right here, and you can just really see why, because this is, this is supposed to be equal amount. It doesn't look equal in my picture, but it's supposed to be. Okay, but this, we're just going to pretend I'm a better artist than I am. Okay, so that is my z-crit. Now, I went ahead and did my experiment, and I got a test statistic, and the z that I obtained was 1.75. Where would that fall here on my curve? Well, if this is positive, right? So this is going to be somewhere right in through here, right? It's not more than positive 1.96. It's less than positive 1.96. This is my z obtained. my Z obtained is not in the area of rejection. Since my Z obtained is not in the area of rejection, then I am going to I'm going to retain the null. Or another way to say that is failed to reject. So I'm going to retain the null. Or another way to say that is failed to reject. Okay? Because I'm not in the area of rejection. For this example, I'm not going to go ahead and do the probability yet because I don't want to, take out StatCrunch. We're going to do that when we start doing the full hypothesis testing. But I know that my Z obtained is in the area of retention and not rejection, so I'm going to keep it. Okay? Now, what if I had another alpha? Let's try an alpha that is greater. Let's go ahead and try an alpha of 0.1. And for an alpha of 0.1, my Z-crit is going to be 1.64. 1.64. So that means that I'm going to try to do another, let's see, scooch this down. Okay. I'm going to go ahead and make another curve because this one, it wasn't my best, but, I am only human. Okay, so here's another curve. And I'm going to try to make this more symmetrical. And I'm going to put this right in the center. 0, 1, 2, 3, 1, 2, 3, -3, -2, -1. +1, +2, +3. Okay. Now we change the alpha. Now you're not supposed to change the alpha after. You're not supposed to try to reject the null after. That's why you set the alpha at the beginning in the preparatory stage. But I just want to point something out to you. Now, this was the area of rejection when I had an alpha of 5% and my Z-crit that matched that was positive -1.96. Now I'm going to show you what happens had my alpha been 10% instead of the 5%. So now I'm going to have an area of rejection that is that starts with a Z-crit of 1.64. I should probably do this in green. 1.64. So here is going to be my Z-crit. Scooch this up. My Z-crit of positive 1.64. Okay. And down here is going to be my Z-crit of negative 1.64. Z-crit equals negative 1.64. Okay. So this is saying anything above greater than 1.64, I'm going to reject. Anything less than negative 1.64, I'm going to reject. If it falls in between, I'm going to retain. Now my Z obtained, write this in black, my Z obtained that I had from up here, right? My Z obtained that we used in this particular example was 1.75. Well, where does 1.75 fall in here? 1.75 falls in the area of rejection. So in this situation, because my alpha was larger, and this time the same exact Z obtained fell in the area of rejection, now because my alpha was so much greater, I now have enough evidence to reject the null. Okay, because it's in the area of rejection. So do you see how this area is so much bigger? The green is covering more area of the curve than the red. The red alpha, 5%, has 2.5% in the right tail and 2.5% in the left tail. The 10% alpha has 5% in the right tail and 5% in the left tail. It's twice as big. So of course you're going to have a better chance of rejecting the null when your alpha is greater. Okay, now what did you do? You doubled the risk of committing a type 1 error with that. So, you know, if this was some sort of really important study where it's not a good idea to be wrong 1 out of every 10 times, you're going to be in trouble because you're going to have a lot of type 1 error. But I wanted to show you how this would work. Now, I really want to emphasize, you never, ever change your alpha level to try to reject the null. You set your alpha level at the beginning of the experiment and you keep it there. Let's see what happens when we have a left-tailed hypothesis, okay? And see how we go about retaining and rejecting. When you have a left-tailed hypothesis, your null, of course, is always going to be that the expected proportion is equal to whatever expected proportion you were given for the null, whatever it is believed to be in the population. Your alternative hypothesis is you want to know if the treatment has decreased the proportion. Okay, so after whatever experiment you're running, has the proportion significantly decreased from what is expected in the null hypothesis. When you decide on what your alpha should be, all of the alpha level is going to be in the left tail. It's all right here. This is no longer divided up like it was in the two-tailed hypothesis. All of it is in the left tail. So if you have a 5% alpha, 0.05 alpha, then all 0.05 is going to be in the left tail. If you have a 0.01 alpha, 1% alpha, then the whole 1% is going to be in the left tail. Okay, because we're only concerned with what is significantly less than the expected population proportion. So we're going to continue our discussion just using the 1% alpha. So we're just going to say that the significance level is 0.01, and I'm going to look at my table to find my Z-crit for my left one-tailed hypothesis test. And my Z-crit is going to be right here, marking the area of rejection, so that I know that anything less than this Z-crit will be the area of rejection, and anything more than that Z-crit is going to be the area of retention. So if I get a test statistic that's less than my Z-crit, I'm going to reject. And if I get a test statistic that is greater than my Z-crit, I'm going to retain. Okay? Now, I'm also going to make sure that the p-value, the probability of obtaining that test statistic, is less than my 1% in this instance. If you had a 5% alpha, then it would be 5%, whatever. But in this instance, I'm going to make sure that my p-value is going to be less than my established alpha. And as a reminder, what the p-value tells you is that it is a probability. That means that if the null hypothesis was true, then the p-value is a probability that if you were to repeat this, you would get a test statistic that is that low or even lower than the one you actually got. Okay, so we're looking for a small p-value that suggests a surprising outcome and would completely discredit your null hypothesis, meaning that you established a threshold for rejection and it has passed that threshold, so you're going to go ahead and reject. The threshold that you've set is the risk that you're willing to assume of committing a type 1 error. That is, falsely rejecting the null. So let's look at the different Z-crits and what that means in terms of rejection. So if you were working with a left one-tailed hypothesis, and you had a very serious situation. You were working with a situation where a high significance level would be a bad idea. It's better to just commit a type 2 error than risk committing a type 1 error. Let's say you have a significance level of 0.001. Your z-crit is going to be negative 3.09. Okay, it's only negative because we're just concerned with the left side of the curve, right? This is just looking at something that is much, much less than the expected null. So our negative 3.09 is going to be way over here. There is such a tiny, tiny piece of the shaded area, the alpha, where you would have to reach in order to reject. For a 0.01 alpha, you are going to use the z-crit of negative 2.326. So if you had your z-crit of negative 2.326, your z-crit would be maybe over here about, okay? And the whole 1% would just be out here. So if when you finish your study, so your obtained z-score for your study is less than negative 2.326, then you're going to reject. If it's more than that, then you're going to retain. If you were working with a significance level of 0.05 and you were working with a left one-tailed hypothesis, right? You're looking for things that are much, much lower, much, much less than the expected proportion, then you're going to use the z-score of negative 1.645. So then you're going to be maybe somewhere around here, and anything less than that, you're going to reject. If you were to obtain a z-score with your results less than negative 1.645, you're going to reject that. Anything more than 1.645, you're going to retain the null. Finally, if you were working with a significance level of 0.1, where you're risking committing a type 1 error 10% of the time, meaning 10 times out of every 100 trials, and you were working with a left one-tailed hypothesis, then your z-crit would be negative 1.282, and anything less than negative 1.282 would be in the area of rejection, and you would consider that enough evidence to reject your null hypothesis, and anything more than that would be considered not enough evidence to reject the null, and you would retain the null, or another way to say that is fail to reject the null. Let's look at an example on Ziteboard again. So I'm going to try to keep this simple using the same scenario from example to example. In the last example that we used, we talked about how the question had to deal with just a change from 17%. And the question was, has the proportion of the population that prefers red cars changed from 17%? And that's why we used the not equal to sign. Now we're working with the same scenario, but this time we are working with, has the proportion of the population that prefers red cars decreased? Okay, this time we're working with decreased from 17%. So my alternative hypothesis is going to say, has the proportion decreased from 17%? And I went ahead and, just for the sake of all of us, I went ahead and prepared by making my curves in advance. And I also prepared by writing down the alpha levels for 0.05, which is the same thing we did the last time, and an alpha of 0.1 as well. Here I've written the z-crit that matches that alpha. So in this bell curve, I'm going to go ahead and mark the z-crit of negative 1.645. So here's negative 1, and so negative 1.645 is going to be about here. And I'm saying anything that happens below out here, I'm going to reject. Now, my Z obtained, I'm going to continue to use as I did before. When I did the experiment, I found that my Z obtained was 1.75. Well, 1.75 is a positive number. It's way out here. That's my Z obtained, or my test statistic. Here it's very obvious that is in the area of retention, right? Because everything from Z crit and above, I'm going to go ahead and retain. And everything less than my Z crit, I'm going to reject, right? So my Z obtained ended up being in the retention area. So here I would retain the null. Let's see what would happen with an alpha level of 0.1 for a left one-tailed z-test. Well, let's mark my area of rejection. I've got an alpha of 0.1. It's a one-tailed, left-tailed test. So I'm going to go ahead and mark my z-crit at negative 1.282. And that's going to be just a little bit closer to 1 than the last one. Okay? And everything less than that, I'm going to reject. So this is rejection. And everything more than that, I'm going to retain. Okay. Well, what was my Z obtained? My Z obtained was 1.75. So this time it didn't really matter, right? My Z obtained equals positive 1.75 because neither one of them were in the area of rejection. Let's just do one more as another option. I'm going to say my Z obtained, instead of it being 1.75, I'm going to say my Z obtained was negative 1.52. Well, this time I'm going to be here at negative 1.52, that's going to be a little bit more here, right? Because this line right here, the red one, that was my Z crit. Okay, that line right there that we had matched, that was for my Z crit of a 5% alpha, which is negative 1.645 for a left one-tailed test. And my Z obtained that I used in my little orange example here was negative 1.52. So in this situation, had my Z obtained been this, then I would still retain because it's close, but it's not past the Z crit into the area of rejection. So in this case, I would still retain. Now let's look at what happened with this one right here. This one, my line was so messy with that one that I didn't even realize that it was a straight line. Okay, so here my Z crit was negative 1.282. Here in this situation, if I were to go ahead and plot my Z obtained, it would actually be in the area of rejection. Okay, so in this situation, I would have rejected the null of no difference. Okay, so again, I want to stress, just like I did the last time, that you never change your alpha levels. The point of me showing you the changes in alpha levels, right, is just so that you can see how sometimes you reject and sometimes you retain. It depends on what your alpha level is at the beginning, right, the threshold that you've set in order to avoid making a type 1 error, and where your test statistic, in this situation we're using our Z obtained as our test statistic, falls in relation to your Z crit. Okay, so we're finally at the last hypothesis test, and this is a right one-tailed hypothesis. The right-tailed hypothesis is just the opposite of the left-tailed hypothesis. So everything that we did in the last one where everything was negative, now we're going to be looking at things where everything is positive. But the same thing exactly happens, except it's going to be on the other tail. Again, the null hypothesis is just going to be the proportion of whatever we think the population proportion is, what it's stated to be. In terms of the alternate hypothesis, we're looking to see if the proportion in our sample is going to be greater than the expected proportion. This time, all of the alpha level is going to be in the right tail. So if you have a 5% alpha, all 5% will be in the right tail. If you have a 10% alpha, all 10% will be in the right tail. So for a right one-tailed hypothesis, we are only concerned with values that are significantly more than the expected population proportion. For the sake of our discussion, we're going to continue just working with the 10% alpha, 0.1 alpha. Just like before, I have to mark my area of rejection. So I'm going to look at the table of Z-crits to see what matches my alpha so that I can mark where the area of rejection starts. This way I know that once I calculate my Z obtained, any Z obtained that falls above my Z crit will be in the area of rejection, and anything to the left of that Z crit or less than that Z crit will be in the area of retention. So because this is a right one-tailed hypothesis test, anything greater than my Z crit will be rejected. Anything less than my Z crit will be retained. The other thing that I'm going to do is I'm going to make certain that the p-value of my Z obtained, right, of my test statistic is less than my alpha. As a reminder, p-value is a probability. It's the assumption that if the null hypothesis is true, the p-value is the probability that if you did this experiment again, you would get a Z obtained that is as extreme or more extreme than the one you got. So it would be at least that Z statistic, or because this is a right one-tailed hypothesis, it would be one that's even greater. The smaller the p-value, the smaller the probability. That suggests that this is a very rare occurrence, and it would be enough evidence to discredit the null hypothesis and reject it and assume that the alternate hypothesis is true. You compare your p-value to your alpha. So the alpha is the amount of risk you're willing to take, 10%, 5%, whatever. So if your p-value is less than your alpha, then you have met the threshold that you had set in order to reject the null. Doing this allows for the control of type 1 error, that is falsely rejecting the null. So let's look at our Z-crits for a right one-tailed hypothesis. Now, if these look at all familiar, they should. We used the exact same ones for our left one-tailed hypothesis, but in that version, we used the negative values. In this, we're going to use the positive values because we're only concerned with the greater than. If you have a significance level of 0.001, that means that your Z-crit is going to be 3.09, so it's going to be way out here. If you obtain a Z-score in your sample that is greater than positive 3.09, you will reject the null. And if you do not meet that threshold, then you will retain the null. For a significance level of 0.01, your z-crit is positive 2.326. So you're going to have your z-score more or less right here. That's going to be the z-crit in this right one-tailed hypothesis for proportions. If you got a z obtained that is more than 2.326, you're going to reject the null hypothesis. And if you get your z obtained from your sample that is less than 2.326, then you're going to retain the null hypothesis. If you're working with an alpha level of 0.05, your z-crit will be positive 1.645. In this case, the z-crit is going to be more or less right here. Anything greater than 1.645 will be rejected. So if your z obtained is more than 1.645, you will reject the null hypothesis. If it is less, you will retain the null hypothesis. And then finally, for a significance level of 0.1, in other words, 10% alpha level, in other words, 10% risk of committing a type 1 error, which is rejecting the null when the null should have been retained, your z-crit is going to be positive 1.282, and it's going to be more or less right about here. If you get a z obtained in your sample that is more than positive 1.282, you will consider that enough evidence to reject the null hypothesis. And if you get something that is less than positive 1.282, you will retain the null hypothesis of no difference. Let's go to Ziteboard and do another quick example. Okay, so here I am back in Ziteboard. I just want to give you a reminder of what it looked like when we had an alternate hypothesis that was looking at a decrease from the population proportion, and how we marked the area of rejection. We looked at everything that was less from the z-crit. Now we're going to be doing the exact same thing, but this time we're going to be looking at everything that is greater than the z-crit. So here I've written everything again. So this time the alternate hypothesis is asking the question, has the proportion of the population that prefers red cars increased? So this time it says increased from 17%. And we can see that here our alternative hypothesis has the greater than symbol. To save time, I've done the same thing. I went ahead and wrote down the information for an alpha of 0.05, the z-crit for an alpha of 0.05 for a right one-tailed hypothesis is positive 1.645, and I did the same thing for an alpha of 0.1, and in that situation, the z-crit for a right one-tailed hypothesis test is positive 1.282. So let's do the 5% alpha first. So 1.645 is approximately here. That is my z-crit. And I'm going to mark the area of rejection, everything to the right of my z-crit, because I'm looking at anything that is greater than my z-crit. So now let's look at my z obtained. My z obtained I kept the same. My z obtained here was positive 1.75. So positive 1.75 is going to actually end up being out here. This is my z obtained equals 1.75. And you will notice that it is in the area of rejection. So here I'm going to go ahead and reject the null of no difference. Let's look at an alpha level of 0.1. The z-crit is 1.282, and that's going to be somewhere about there. I'm going to scooch this up a little bit Actually, I'm going to make it just a little bit smaller. Maybe I can fit. Yeah. So the z-crit here is going to actually be positive 1.282. Everything greater than that is going to mark my area of rejection. Okay, so everything on this side, I'm going to reject. And everything on this side, I'm going to retain. I did the same thing over here, but I forgot to mark it, so I'll go back and mark it real quick. Everything to the right that is greater than my z-crit, I'm going to reject. And anything that is less than my z-crit, I'm going to retain. Okay, and my z obtained for my 5% alpha fell in the area of rejection. Well, look what's going to happen here. If this one got rejected, this one's definitely going to get rejected, because this is my z obtained is here. It is in the area of rejection. No question about it. So in this situation, both of them came out to be rejected. Now, if I would have had another z obtained, let's just say my z obtained was 1.00. Okay? In this situation, here's my z obtained. I would have retained the null hypothesis here because this is in the area of retention. Same thing would have happened in this situation here. I still would have been able to retain this because in this situation, the number that I happen to pick for this example both happen to be in the area of retention. It's important to note that your p-value in these situations where you reject, your p-value has to be less than your alpha. For a right one-tailed alpha, your z-crit is going to be less than your z obtained to reject, and your p-value is going to be less than your alpha to reject. Whether you're working with a two-tailed hypothesis test, a left one-tailed hypothesis test, or a right one-tailed hypothesis test, one thing is always true. If the p-value is less than alpha, then you should reject your null hypothesis and accept that there is sufficient evidence for it to be likely that the alternative hypothesis is correct. If the p-value is greater than your alpha, then you should retain or fail to reject. Means the same thing, retain or fail to reject, but you should retain your null hypothesis. There is not sufficient evidence for you to reject it. One thing I want to mention that is easy, it's very easy to do. You always want to state that the null hypothesis is rejected because there is sufficient evidence that the alternative hypothesis is correct. You should not say that the alternative hypothesis is proven or true. You should just say that there is enough to reject the null and for the alternative to be accepted. If the p-value is greater than the alpha, then you should state that you retain the null or you fail to reject the null. You're simply stating that there is not enough evidence for the conclusion to be made that the null should be rejected. Finally, never state that the null hypothesis is accepted or true. It's possible that the power is too small and the H0 is still false. In other words, there's still a possibility that you are committing a type 2 error, But because your sample size is too small, it cannot be determined. The only way to increase power is to increase sample size. It's always possible that there was insufficient power for you to be able to detect an effect when one actually existed. So what's the big idea? Today's big idea is that researchers must decide ahead of time how much they are willing to risk in committing a type 1 error. The amount of risk is described by the level of significance, which is denoted by the Greek lowercase letter alpha. The line which marks the alpha is called the critical value. It's the mark where we know alpha begins. The test statistic is the z-score of the results, and the p-value is the probability of obtaining the test statistic. The other big idea is that in order to reject the null, the obtained p-value must be less than alpha. If the p-value is less than alpha, you should reject the null and accept the alternate. If the p-value is greater than alpha, then you should retain the null and state that you do not have statistically significant evidence to make a conclusion. So that's it for today. With that said, don't forget to check your emails, check Blackboard, do your homework, and subscribe to this channel. Even better, hit that notification bell so you know when there are new videos for this course. Okay? This is your teacher, Taurus, saying stay safe, and I will be waiting to give you a virtual elbow bump in the next video. Ciao!